Many often we would like to visualize a relationship between variables. And we've looked at the regression analysis as a way to model a relationship between an outcome and a set of predictor variables. So on top of a scatter plot, which is the basic way of visualizing a relationship between two variables, we can actually visualize this relationship by reflecting upon a linear model interpretation. In a kind of a very basic version of this, we can plot a line that represents the regression line when we've got two variables. But there are more advanced ways of customizing this relationship and also incorporating other predictors into the equation. Seaborn comes with a set of regression visualization options which nicely complement doing regression analysis with stats model that we've seen before. So let's take a look at some of these options. So let's start by just looking at really the basic. Seaborn has two functions, regplot and lmplot for regression and linear model plot. They're related, but they provide different options. So they may be important to use the function that suits the particular task. But let's start with a basic model, which is showing a relationship between two variables. So for example, let's say I want to show the relationship between total bill and tip. In this case, we can use a regression plot and we can see the scatter representation here as well as a linear regression line with a 95% confidence interval. With linear model plot, we have a different but very similar representation. One of the changes that we can see here is that linear regression plot kind of spaces both the x and y axis equally to get kind of like a square visualization. That's actually something you can achieve with a regression plot by setting the size of the plot. But a linear model plot also incorporates other options that makes it more versatile to showing different kind of relationship between the two variables in question. And thus linear model plot is kind of designed more to emphasize the relationship than to basically reflect upon the two variables and the exact values of these, the values from the data. So let's take a look at some of the options that we've got with linear model plot. If one of the variable is a categorical variable such as size, we will face the same problem that we've seen with cat plot, and that's all of those points are going kind of to overlay. It's become more difficult to show their distribution. We can actually add jitter to the chart to linear model plot. Very similar to cat plot, we can add random jitter here. And the more jitter we add, the more kind of spread out these points will become, as we can see here. Another option here is to actually aggregate all of these points and to add a confidence interval across the mean. So we can do a linear model plot, x size and y in tip, but then tell Seaborn to estimate the x using the mean. And then we've got the mean and the confidence interval, and that will be useful to show a general relationship as well as the spread out of the data points over each one of these different values of size. Now, so far we're looking at a linear relationship, but very often we want to model a different kind of relationship. So let's load this data from Seaborn. This is another classic data set called anscom. This is a data set which is designed to be, two variables are designed to have exactly in each one of these data sets identical descriptive statistics, and hence the value of visualization in showing the relationships across the different kind of relationship that those two variables have across each one of those different categories. So let's look at the first subset of the data set, subset 1. In this case, we've can see that we've got a linear relationship between x and y. Now, if we look at the second subset, you can see that the linear relationship is exactly the same. The estimated regression line is exactly the same, and that's because this dataset has been designed so that those different subsets have exactly the same descriptive statistics. But we can obviously see that the relationship is not linear, right? If you look at the scatter plot, you can see it's kind of a quadratic here. So to do a quadratic relationship with either LM or reg plot, we can tell it that we're looking at the second order relationship instead of a first order. So in this case, we got a quadratic relationship, which actually a good fit, a perfect fit to the data, simply because the data has been generated that way. So that's the first order, that's the second order, and obviously I can go to a higher order relationship, which in this case seems good enough, but it's actually overfitting the data. Another issue with linear model is that they're very sensitive to outliers. So if you look at the dataset 3, we can see that we've got a relationship, a linear relationship between x and y. If you look at the scatter plot, the dots. But there is actually one outlier which is skewing the regression line a lot. So that's an issue with linear models. They're very sensitive to outliers. To deal with this, we can fit a robust regression which actually compensate for the existence of outlier by the way it kind of estimates the residuals. So turning robust to true is going to estimate a regression line which is actually not sensitive to this big outlier here, as we see. So the default for robust is to be false. We can turn it to true to deal with outliers. All right, so let's say we got a binary outcome, a binary y variable. We can still fit a regression line, but the problem with this regression line, as we've seen when we looked at logistic regression, is that it extends really without any bounds, which means it's creating implausible predictions. So big tip is binary 1 and 0, but with a regression, it's possible to predict big tip as any value actually, in between minus infinity and infinity, which doesn't have any useful meaning when it comes to this data. Now, instead, what we've seen with logistic regression is to kind of to smooth this linear function with the logistic functions to kind of bound its value in between 0 and 1, and that's basically also has a probabilistic interpretation using the odds ratio language. So in this case, we can do the same. We can tell linear model plot to use the logistic regression instead of linear regression. And you can see that now we have a logistic function. It's kind of like an S-shaped function. And the value here, the predicted value, so for example, if total bill is 20, the predicted value is 0.6. What this means that the odds ratio of 1 to 0 is 0.6. So it's more likely for the tip to be big than to be small in that case. We have more options for customizing the relationship between the x and y. Another option to incorporate a completely non-parametric approach. So a parametric approach to regression means that we've got a parametric form. For example, y equals to beta of x plus beta 0, or if you do quadratic, maybe if it's beta 2 times x squared plus beta 1 times x plus beta 0. So there is a form in which it gets parameters, and we are estimating these parameters. Another way is to go completely non-parametric, and one of those approaches here is lowest smoother. I'm not going to talk about this in detail. You can check the Wikipedia page on local regression, but you've got a regression line which kind of more customly attuned to the local areas than fitting a global regression line across all of these different points. Very often when we do a regression analysis, we're interested in plotting the residuals. And the residuals are important because they tell us whether our regression creates good predictions or not. The better the prediction, the lower the residuals. The residual is the difference between the true value and the predicted value. So that also gives us an idea about the goodness of fit of the regression model. So let's take a look at this with the first subset of the anscom dataset, in which really the dataset was linear. Here you can see that you've got residuals, many of them around zeros, but you still get residuals from -2 to 2. Now, if we do the same, and still assuming a linear regression, and then we do the subset 2, unfortunately here you've got much larger residuals. That basically tells us that a linear model may not be the best model in here. All right, so far we have been looking at only a relationship between two variables. But many often we have more variables in our data that we want to incorporate in a regression analysis. So very similar to using color in the graph to add yet another categorical variable into play, we can do that with regression plots. In this example here, we are plotting the tip and the total bill in a linear model plot, but we want to estimate two different regression lines for smokers and non-smokers. So we use hue, mapped it to smoker, and that basically will create two overlaid graphs, one for smokers and one for non-smokers. Now here we see something very similar, except that we added markers and we changed the palette. This is kind of a more advanced example of customizing the plot. Now, color and those markers are important for two reasons. One of them is when the chart is to be reproduced in a medium different than screen. So that's important, for example, if the chart is to be printed out, or if you're producing a chart for a black and white screen, such as a screen for an e-reader. You want the colors to be contrasty, and you want to have a marker to compensate for the lack of color if that's was kind of also a potential outcome. The second kind of reason why this may be important is when we're kind of promoting our visualization to be understandable or clear to people with visual disabilities, such as colorblind people. And then it becomes important to pick the palette so that we've got larger contrast than the regular one. Now, let's say we've got more than one or two variables that we want to put in our chart. So what do we do in this case? Well, in this case, we use color for one variable, which is smoker, but don't forget that we've got more channels. So we can actually use this faceting to map the columns and the rows or the rows to other variables. So for example, here you can see that we've used the column faceting to produce the same plot for time lunch and time dinner. And here we've done the same. But we also conditioned on another variable, which is male and female. So we've got the columns here being mapped to time, lunch and dinner, and the rows being mapped to sex, male and female. So we've got a regression line for each one of these subcategories per smoker, yes and no. And again, the value here is that you can compare and contrast the different set of relationships here when you look at these two different subsets. The confidence intervals are also important because they show you also the kind of the variance across the regression line. And here you can see that you get huge confidence intervals that are completely overlapping. So it's hard to say that smoker and non-smoker differ. And actually all of them across except probably this one. Now finally, we have many options to control the size and the shape of the plot for both regression plot and linear model plot. So I'm not going here to go over all of the details. We can customize the figure size, as you can see here. We can also customize the facet size. and the aspect ratio of those different charts, and that is important if we are creating a chart for kind of a professional or in a production environment. Now finally, in addition to regression plot and linear model plot, other plots in Seaborn have a regression option to create a regression line. So this is a joint plot which does a scatter plot and also a distribution plot across the two axes. And we can put the kind regression to create a regression line. So that's nice because it condenses 4 different kinds of plots in one plot. You've got 2 histograms for each one of the 2 variables. And actually you've got a kernel density estimation here for smoothing the histogram. And then you've got the scatter plot, and on top of it, a linear model plot. And the same thing can be done with pair plot. So the pair plot will show us the relationship between one variable and 2 or more other variables. So in this case, we've got tip, which is common on the y-axis, but then we kind of stack 2 variables on the x-axis, total bill and size. And in this pair plot here, we also specified kind to be a regression, so we get a regression line as a bonus. Without that, we get a basic scatter plot. And we've got access to the similar set of functions, such as changing color by mapping hue to another variable such as smoker. There are more options. I'm going to stop here. I advise you to take a look at the tutorial and also the gallery, but this serves to illustrate kind of the versatility of regression model plotting with Seaborn, which is a nice complement of creating regression models using stats models.